All right, so what I have here, boys and girls, is I got myself an absolute zero demonstrator. It's really a Bourdon tube. It's got that little copper, flattened out copper, that basically as the pressure increases, what happens to that copper? Straightens out, and as the pressure decreases, it's really another form of manometer. But this is not gauge pressure, so this is actually reading the pressure that's of the air that's in this sphere. This is a steel sphere, so we've got a fixed volume. We have a certain number of moles of gas, and I just opened up and exchanged the air with the atmosphere, so I'm reading the atmospheric pressure. Now this is not torr, torricelli's, or millimeters of mercury. What you see here is PSI. PSI is pounds per square inch. It's another value. 14.7 pounds per square inch is another equivalent to 760 torr, or atmospheric pressure, or standard pressure, as I say. So, reading up here, it looks to me that I've got, let's see, 11, 12, 13, 14.6. Okay? So I got about 14.6 PSI. So that's almost standard pressure, okay? Very close, which we'd expect to be around. So what we're going to do here is we're going to drop this into liquid nitrogen. Now, I want to calculate what the pressure would be in this sphere when we get to the temperature of the liquid nitrogen. Now, liquid nitrogen boils at negative 196 degrees Celsius.
What temperature is it then?
Well, when something boils, isn't it?
Before boiling. What's before boiling?
Well, it could be any temperature from absolute zero, correct? So it's a liquid. But right now, isn't the room way above 196? Yeah. So therefore, the liquid nitrogen's boiling. Its limits of how hot it can get is its boiling point. So the temperature of the liquid nitrogen is still 196. Now, it could be off by a little bit because we're not at perfect atmospheric pressure. Pressure does affect boiling points, as I'll talk a lot more today. But that's pretty darn close. What's that in Kelvin? What's that?
77.
Yeah, so that's 77 Kelvin. So let's do no degrees because Kelvin used the Celsius scale. So what I want to do is let's calculate, okay, what the new pressure would be. Now, if we think about the relationship, we can do PV equals nRT, but I can use the combined gas law formula. I can use VP over T, which equals VP over T. Remember, this is the current condition, and this would be the new condition. Now, what's going to be supposedly constant in this equation? Yeah, the volume is fixed. So because it's constant, I'm going to get rid of that. And now I have this relationship. This is kind of like what we do in Regis chemistry. Now, what's the current pressure? Well, I'm going to use PSI. I'm not going to use the universal gas constant, so I don't have to convert. I'm just going to do basically somewhat of a portion here. And remember, how did we get this? How did we get VP over T, right? We got this by doing our derivations. Okay, so in any case, let's solve for this. We have the pressure initially is 14.6 PSI. The temperature, of course, has to be Kelvin. As we do every gas law, we have to be from an absolute standard from zero. So this is 77 units of temperature from zero. And what we want to do, I'm sorry, we're starting at room temperature. So I can't use that. So that's going to be our final temperature. Thank you. Okay, we're going to solve for the new pressure, but what do we need? We need a temperature. So I'm going to go look at my thermometer. I got a little one there, but that's hard to read. Okay, nothing against smaller thermometers. So I've got a thermometer somewhere. Did I have one up there? There's always something I forget. Okay, so good. So there's my thermometer.
He just said that one's hard to read.
It's too small, yeah. So this one, the thermometer is giving me a value. Make sure I read it correctly. And I'm getting 20, looks like 20.9. So 20.9. Now 20.9 degrees Celsius, that's our room temperature. 20.9 degrees, what's that in 293.9? Okay? Okay, so let's do our math. Pretty simple stuff here, party people. Okay, to solve for pressure, this is going to be what? Rewriting this, pressure is equal to 14.6 psi times what?
77.
Times 77 Kelvin over 293.9 Kelvin. Notice what's going to cancel? The kelvins. Okay? Yep. So we do the math. What do we get? 77 divided by 2, 9 to 3. 0.9 times 14.6.
Okay.
I get 3.8. I'll just do 2 sig figs because it's 77 Kelvin. 3.8 known as psi. Okay? So I expect 3.8 psi. That's pounds per square inch. That's the unit of pressure I'm using.
Where'd the 20.9 fit in?
That's the room temperature. This is the current condition. So the pressure in the room, or the current pressure in the sphere, is 14.6. The current temperature in the room was 20.9 degrees Celsius. We're doing a gas law, so it has to go in Kelvin. So that's what this is. I converted to room temperature, the initial, and now when I drop in the liquid nitrogen, I want to see if that gauge goes down to 3.8.
So
Now,
the 20.9 degrees Celsius is the 293.9.
right, I converted the room temperature to Kelvin. Okay, so let's stop talking about it. Let's do it now. What are we trying to test? I'm trying to see if my gases are behaving ideally. So,
Merry Christmas.
yeah.
It's a very abundant source of lithium.
Yeah. Thinking about that.
We've been using it for like a week.
I feel like you poured it. Yeah, for the thing is endless.
Is that a really heavy thing?
Oh yeah, it's a heavy.
You're strong.
Been working out. I do 15 jumping jacks every day. Okay. But then I do the small circles, and that really works me out. Okay, so the small circles do anything anyway. Okay, I'm warmed up now. To warm you up for the big circles. Oh yeah, can you imagine going big circles first? Oh! Didn't do my small circles. All right, sorry. All right, so let's drop this and see what the pressure. We'd expect what? To go down to 3.8. Gotta hold it down because there's air in the sphere, and it was kind of giving me a buoyant effect. As I submerge something, it gives me a buoyant force. It's kind of like how our hot air balloons are going to float when we make them.
If you put like a drop of like food dye in there, would it be green smoke or whatever? color?
No, because all we're not going to. That smoke, of course, is nothing more than fog. So we
Okay.
can't really color the water vapor. We might.
If you made like a colored liquid nitrogen, wouldn't the gas that came off?
It's going to be hard to do because we're talking about the temperature at which the water actually is, in this case, condensing, which would be a different temperature for the dye, even though there'd be probably some of that. Okay, so am I anywhere near? Oh, I'm getting somewhere, aren't I?
Yes.
Okay, now, am I at 3.8? Let's see. Okay. 1, 2, yeah, I'm on, right on the 4 line.
You're almost there.
Now, of course, sometimes with a gauge like this. And there's also limitations. These gauges aren't meant to be all that precise, or accurate, I should say, at these temperatures. Okay, but I'm definitely under that line. I don't know if you can see that. Okay, but that looks like 1, 2, 3, 3.8. Okay, so it's under that. But it's not what I wanted. I wanted to show you that there's real gas behavior. So I'm like really upset now. I'm keeping it in. But I didn't. What I expected this number to be what? Above that. Why? I should not have gotten what my math, my gas law has given me, because gases do have some real behavior, which mean what? They actually do attract. If you can do anything with the kinetic molecular theory, think about attractive forces. That's where everything goes here. Gases have some attractive forces. Now, my friends, as the temperature drops, we know the gas molecules move what? Slower. As they move slower, don't they have a better chance to attract? So I would expect the pressure okay, not to be 3.8. Now, actually, what I expected is that some of these gas molecules are now liquid. I expected this pressure to be higher or lower.
His pressure? Higher.
Lower. If I slow down the gas molecules and they're now working in unison and they're not no longer independent random particles, are they going to hit the container walls with the same force? No. Instead of moving in straight independent paths, now they're curving to go together. This one should have hit the container wall, but now is traveling longer to get there. We call that mean free paths. So what I'm trying to say to you, party people, so in the sphere, gases should have hit the container wall right there independently. But what's happening is this gas is going, hey, I like you too, and now they're doing what? They're bending. And now it takes what? Longer time to get to the what? Container walls, which means the pressure drops farther. So we always get a lower pressure than expected because of the behavior. But I'm not getting it. But am I?
Yes.
Right, RMA, right. So I should have gotten a pressure lowering effect. But let's think about this for a second. I'm using pressure and temperature as my factors. What must stay constant? Number of moles in the sphere and the volume. I had a steel sphere, party people.
Oh, what it goes down.
Right. So my steel sphere definitely did what? Got bigger or smaller as it cooled. You know this because if you go over a bridge, what do you see when you ride over a bridge? You see that teeth, right? You'll see this in the road and the bridge.
Where?
These are expansion gaps right over where you ride over. So you're going to ride over some metal gaps, and these are teeth that allow it to expand in the wintertime and pull back in the summertime so that the what? The bridge doesn't buckle. So you'll see this on the road, on the bridge itself. You'll see these little teeth, and those are expansion gaps that allow for contraction because of solids. They don't move a lot, but enough in a big bridge it could make the bridge buckle. So there's definitely, even though I'm not measuring here, that sphere got what? Smaller. If the sphere got smaller, what happens? The volume got smaller, which happens, what's that going to do to the pressure that remains? So I'm actually having elevated what? Pressure that's making me look like that I have an ideal gas. You see that? Okay, so the smaller volume bumped up my pressure enough to make me think, positive proofing here, or a false positive, that I'm at where I'm supposed to be. Okay, but interesting enough, I don't know if we can hear it, or we'll see when I pull this out in a second, that oxygen, now liquid nitrogen is negative 196, oxygen is negative 180 something. What does that mean? Who isn't liquid oxygen have a higher boiling point? So therefore, shouldn't this cold liquid nitrogen make the gas molecules not only act like real gases, actually condense into a liquid? And if they condense into a liquid, what happens to the pressure? Right, it drops. The pressure is not what you expect because all gases will condense. So I don't know if this is going to work, but I'm going to pull this out, and I'm going to try to do is shake it like a Polaroid picture, and I'm going to see if, in fact, we hear a liquid. If the liquid splashes around, we have liquid oxygen. I don't know. It doesn't always work. So let's, okay? Let's see. I don't know if it's just the metal inside doing it, but in any case, what's also fun with this is we raise this up, like Josh Groban would say. Okay? And that's a pretty cold sphere. Interesting. This has nothing to do with the demo, but I find it just fascinating. I'm going to pour cold water on something very cold. Water makes the instant ice.
Whoa. That's so cool.
I'm rooting my top there, but hey, I'm tall. So in any case, rock on.